Okay, let's start today's lecture. In the last class, we have studied about synchronous sequential circuit analysis, Mealy machines, Moore machines, and we have studied about the state reduction, why it is needed, and when it is done, when two states are equivalent, and these states are said to be equivalent if with the same set of input they are giving the same output and goes to the same next state, then a particular two or more states are known as equivalent states, and these equivalent states are the redundant states. And when there are more than two redundant states, and these states can be removed or can be merged. So with this example, we are going to discuss how the state reduction takes place and how it will affect the circuit design of our final design given in the problem. So suppose we are giving this state diagram, or we have just designed the state diagram. So here we have A, B, C, D, E, F, and G. These are 7 states. We have one input and one output. This is a Moore type of machine. This input oblique output. So the interpretation is like this. If a particular machine is in state A, if the input is 0, then the output will be 0 and it will stay in state A. Now in state A, if the input is 1, it will go to B and the output will be 0. So with the help of this state diagram, we can conclude the state table. And the state table is, we have all present states A to G. For the particular set of input, here as it is only a single input, then the two combinations of the input will be 0 and 1. And we have outputs for input 0 and input 1. So I have denoted X as an input. Now if let us see if the machine is state D, so here it is D. If the input is 0, if the input is 0, output is 0 and it goes to state E. So with the input present state D, X is 0 goes to E, with X is 0 and the output is 0, like this. So with the help of the state diagram, we can directly conclude the state table. The state diagram is a pictorial method and the state table is a table method to represent state transition of a particular design. So let us do with the state reduction. Suppose we have an input set 0, 1, 0, 1, 0, 1, 1, 0, 1, 0, 0. Now we have to analyze this particular input set, that how the output will be there and how, in which state the machine will go when we give a particular input set. So it is an arbitrary input set 0, 1, 0, 1, 0, 1, 1, 0, 1, 0, 0. So we are going to analyze that how the machine will react to this particular input set. So let us start. Suppose machine is in state A. If the first input 0 is given, first input is 0. So with A, if the input is 0, the output is 0. So input is 0 and the output is 0, and the next state is A. So the next state is A. Now with A, next input is 1. So here next input is 1. If the input is 1, present state is A, then the next state is B and the output is 0. So I have noted down here output is 0 and the next state is B. With the B, now the system or the machine is in state B and the next input is 0. So in B, if the next state is 0, you can look directly from the state diagram or directly from the state table. Both are equivalent, both are same. If it is state B, if input is 0, the next state is C and the output is 0. So next state is C and output is 0. Next input is 1. Here it is 1, the fourth input. Machine is in state C. Machine is in state C. If the input is 1, then the output is 0. So input is 1, output is 0. And the next state will be D. So here is the next state D. Now input is 0. In D, if the input is 0, output is 0. So if the with D, input is 0, output is 0, and the next state is E. So next state is E. Now the input is 1. With input 1, present state E, the next state will be F and the output will be 1. Next state is F, output is 1, and then now the next input is 1. Here it is input is 1. With F as present state, if the input is 1, then the output is 1 and the next state is F. So here the next state is F. Now when we give input 0, with input 0, present state F, the next state will be G and the output will be 0. The output is 0, next state is G. Now the input is 1. Now G with the input 0, input 1, present state G. The next state will be F and the output will be 1. So output here we have written output is 1, the next state is F. Now the input is 0, with F input 0, next state is G. Output is 0. Next state is G, output 0, and again the last input is 0. With the G input is 0, the next state is A and the output is 0. So we have written output 0 here and the next state is A. So this is the way with this particular set of input 0, 1, 0, 1, 0, 1, 1, 0, 1, 0, 0, the output is 0, 0, 0, 0, 0, 1, 1, 0, 1, 0, 0, and these are the next states followed as A, B, C, D, E, F, G, A. So here we can see that the movement of the output, how the output is changing and how the next state comes when we give a particular set of input. So we have to look, if we reduce this particular state diagram or state table, then we have to see if the output is same and the state moving to the next state is same. If it is true, then we can reduce two redundant states. So in the next slide, we are going to discuss how the reduction takes place. This is known as the partitioning method. So you can see here, if we look into state E and state G, the next state for X, next state is AF. Here it is AF and the output is 0, 1 and again 0, 1. So we can see that state E and state G both are equivalent because for a same set of input, they are providing the same output and are moving into the same next state. So what we can do, we can reduce or we can remove state G or E, and wherever there is written G, it will be replaced by E. So by reducing one state, G is removed, and wherever there is G, because G is equals to E, so here it is G, I have put it G by E. So this is the first step. One state is reduced. Now we are left with the 6 states, and we again look in the same manner how a state can be reduced or not. So if you have any doubt in this particular reduction, then you can write into the chat box. Then I'll counter your problem or your queries. Again, with this reduction, we can see that D and F, the next state is EF in the both case, and the output is again 0, 1. So we can further say that state D and state F are equivalent. I can remove F from the state table, and where there is F, it will be denoted by D. So here it comes. Last state is removed because it is a redundant state. Here are 2 Fs. So F will be replaced by D. So we get further a table with 5 possible states. Now again we'll look if there is a possibility of any redundant state. So here we see for the A and B, because first of all we have to look at the output. The output must be same. So A, B, C cannot be same. because in A the next state is AB, B it is CD, and in C it is AD. These are the three which have the same output 0 0, and same is true for D and E, because for D next state is ED, for E next state is AD. So this is how we got the reduced table with 5 possible states. So this is our reduced table, and with this reduced table we can draw the state diagram like this. So drawing the diagram, we have to write first all 5 present states. So A, B, C, D, E, you can write anywhere. The shape doesn't matter. And with the help of the state table, you look directly into, with particular input set, how the next state is obtained. If the state is A, input is 0, next state is A, and the output is 0. So with A, next state is A, input 0, output 0. Present state A, if the input is 1, then the next state is B and the output is 0. If present state A, next state B, input 1, output 0. In the same way, so for E, if input is 0, next state is A, output is 0. With input E, present state E, input 0, output 0, next state is 1. So whatever written in the state table can directly be transformed into the state diagram. Again, we do the same analysis, and we'll see if with this same input set, whatever we have given in the last reduction, in the starting of this particular example, if we give the same input set, so we have to look if the output is same or not, and the next state is same or not. So here we go. Input sequence is same. So what input sequence we have taken here? It is 0 1 0 1 0 1 1 0 1 1 0 0 1 0 0. So we'll take the same input set with this particular input diagram. Present state A, input 0, next output is 0, and the next state is A. Next input is 1. If the present state is A, input 1, then the output is 0. And the next state is B. Next input is 0, with B input 0, output is 0, and the next state is C. Next input is 1, so with C input 1, output is 0, next state is D. Next input is 0. So D, if the input is 0, the next state is E and the output is 0. Next input is 1. E1, output is 1, next state is D. Next input is 1, output is 1, next state is D. Next input is 0. Output with D, input 0, output is 0, and the next state is E. Next input is 1. With E, input 1, output is 1, next state is D. Next input is 0. With D, input 0, output is 0, next state is E. With E, input 0, output 0, and the next state is A. So here you see what we have done in the last example. So I have a query from the Nishant. Okay, so you can directly see that the output for the both initial state diagram and the reduced state diagram, the output sequence for the same input pattern is same: 0 0 0 0 0 1 1 0 1 0 0, and some reduced state as E was replaced by D and E. These were the F and G, which has been removed by D and E. So the next, what we have done, we have reduced the redundant states, and we are getting the same output, and the system is moving to the equivalent same next state. So this is how the reduction takes place, and we can reduce the number of states, and hence the number of states are reduced. That means we are reducing number of flip-flops, number of logic gates, and finally the circuit diagram we design with the help of sequential circuit analysis that will cost less. So how the next topic, so far we have studied about how the states are reduced. So we have different types of states which are named as A, B, C, D, that is the alphabets. The state assignment says that the state must be coded in the binary values, because our computer or the processor understands the binary values rather than the alphanumerical alphabetical values. So in order to realize with the physical components, all the states must be assigned or must be with the coded binary value, and we have a different type of coded values. Suppose this was the table in the last example we have reduced. We are left with the five states A, B, C, D, E, and we are moving into the some next states, and we have output, single bit output in the form of zeros and ones. So all the present state and the next state must be assigned binary values. So these are the binary assignments, how the assignments is done. So further you can assign a normal binary value 0, 0, 0, 0 for A, 0, 0, 1, 0, 1, 0, 0, 1, 1 and 1, 0, 0. You can assign them as a gray code, and we know that for the gray code, single bit change when we move from one state to the another state. So 0, 0, 0, 0, 0, 1, 0, 1, 1, 0, 1, 0 and 1, 1, 0. And you can assign like one hot assignment. In one hot, or single one will be 1, single digit will be 1, and the rest of the all will be 0. You can directly see for the A, the value will be. So how many states are there? The same number of bits are required. So if we are using 5 states, then the 5 bits will be there, and at a moment only single bit will be 1 and the rest of the bits will be 0. Now sometimes the name transition table is used for a state table when a binary assignment is given. Means whenever we have until unless the states are written as a alphabets, these are known as state table, and whenever a binary assignment is given to the state table, it is known as transition table. So this is the difference between a state table and a transition table. Now, as we have discussed about the synthesis and the state reduction, state assignment, let us move to a design procedure, how a design takes place. So these are the procedures or steps which includes for the design of a sequential synchronous circuit. So you are given with words or timing diagram. The next step, draw state transition diagram, that is the state diagram. Make a state table. Then reduce a state table if possible. Assign binary values to the states. Choose a type of flip-flop you are using. Sometimes it will be given in your problem that you have to design with this particular flip-flop, or if it is not given, then you can choose your own. Then derive simplified flip-flop input equation and the output equations. After choosing the flip-flop with the help of the excitation table, you have to find out the particular set of input set which is required for jumping from one present state to the next state. And after the simplified flip-flop equations and the output equation, you have to draw the logic diagram. So these are the basic 8 steps which are used for the designing, as we have done in case of the counter. Again, this that was a synchronous sequential circuit. So the same process we are following here. And let us do with the help of an example. Suppose we are going to design a circuit with the help of a D flip-flop. So the synthesis word is used when we are going to design. Analysis word is used when we are given the design and we have to find out the state diagram or state table. So given the state diagram, design the circuit using D flip-flop. This is the problem we are given with a state diagram. So we have 4 states, S0, S1, S2 and S3. And you can see in the state we have written state oblique output. That means it is a Mealy machine, because output in the Mealy machine depends on the present state. So here it is missing, a 0 will be there. So if in a state S0, if the input is 0, it will stay in state S0 and the output will be 0 like this. So here we have drawn the present state, input X, and next state. Because there are only 4 states, so we have assigned value 0 0 0 1 1 0 and 1 1 for S0, S1, S2 and S3 respectively. 2 flip-flops are required, 1 input, 8 possible combinations. We have a present state and the next state is assigned in the same way, and we have an output. So this is your present state and the next state table or state table, and whenever a state table is assigned a value, then it is known as the transition table. So the beauty of the D flip-flop is that whenever we are using a D flip-flop, the next state is equals to input D. So we need not to here write down the value of the input from the excitation table of the D flip-flop, because the next state is equals to excitation input. So directly we can solve here 3 K maps, one for DA, one for DB and one for output Y. So our next step will be solve with the help of K map. So DA comes to be AX plus BX, DB is equals to AX plus B bar X, and Y equals to AB. So here is the circuit we have drawn. So this is how a state diagram is converted into a circuit diagram.